time to mute your cell phones at this time, and we'll start in maybe in about another 2 minutes or so. So, well, today is day 2 of our Gyan lecture, and in terms of what we want to cover on the second day, today I want to go through the two-phase hydrodynamic instability, and you will see that without really doing any complex analysis, just looking at the instability theory, you can make predictions with respect to what the diameter of a bubble will be at departure, during boiling, or for that matter, if you have a two-phase flow without any heat transfer also, if you want to predict the size of bubbles, you can sort of use the instability theory to predict the departure diameter, the spacing between the bubbles, and so on. That's the beauty of this linear instability theory. With very simple analysis, you can make complications for you can make predictions for very complicated situations. So, we are going to look at two different instability theories, Taylor instability and Helmholtz instability, and with respect to we'll look at both Cartesian and cylindrical coordinate analysis for these instabilities. And then what we are going to do is then apply these instability theories for maximum and minimum heat fluxes in boiling, or what is known as critical heat flux. And then my intention is in the afternoon to go through the transition and film boiling, and also do a little bit of a primer in terms of pool boiling on nanostructures. What if you make a nanoparticle coating on your heater, right? It becomes a nanoporous coating in one sense. So, that helps to enhance the boiling heat transfer, and you get some very counterintuitive data. So, let's see how much of that I can cover, and then we'll end with a discussion and a tutorial section in the last hour of the day. Okay. Now, in terms of contents that we were covering yesterday, we talked about the homogeneous nucleation theory, and we were sort of discussing the extension to nanobubbles and droplets. Now, in order for us to complete that discussion, there is one other topic that I wanted to go over with you all, and that's the concept of LorenzJones potential. Okay. So, let's start with LorenzJones potential, and then we will start with the instability theory. Okay. So, let's say you have two molecules of the same kind, that are approaching each other. Okay. So, one way to describe the force that's encountered by the let's say two monoatomic molecules as they approach each other is using the LorenzJones approach. Okay. So, let's say you have two molecules of the same type, and let's say they are monoatomic molecules. For example, it could be a helium or an argon molecule, for example. Okay. And so, as these molecules are approaching each other, and let's say the distance between these molecules is r. Okay. Now, one model that's out there is that describes the potential field for the force of attraction or repulsion between these two molecules. Okay. And that's the LorenzJones potential. Now, LorenzJones potential is not a very accurate model, but it just does the job of capturing many of the essential features of this interatomic or intermolecular force fields. Okay. So, a popular one is what is known as the LorenzJones 612 model, okay, where the potential field because of these two molecules approaching each other is described by this model. Okay, it's a 612 potential because it has a r to the power 6 and r to the power 12. There are other LorenzJones potential models out there. You can get a r to the power 7 and r to the power 13 or 14 and so on. Okay. So, it's a crude approximation, but it sort of gives you a good picture of how these interactions happen. Okay. So, if I plot this force field phi as a function of distance r, Okay. So, the graph looks something like this, and so this bottom portion that you see over here is known as the potential well. Okay. So, how do I describe the force as a function of the potential field? Does anybody know? I am sorry, del phi del r. Yeah. So, or I can write it as in terms of the negative of the gradient of the potential field. You see that in electrodynamics also, right? If you have two charges or two electrons approaching each other, you kind of get the same type of model essentially. So, if I plot on the secondary y axis, if I plot the force as a function of distance, okay, so that is my force field, and so the force will go to 0 wherever this gradient is going to 0, right. So, my equilibrium force or my equilibrium location is where the force goes to 0. Okay. So, and where does the gradient of the potential go to 0? It is at the bottom of this potential well, right. Here I expect the gradient to be 0, is not it. So, my force at this location will be 0. Does that make sense? Okay. So, let us see. So, if I plot my force here will be negative if I go to the right of this direction, and the force will be positive if I go to the left of this direction. Is that what it is? Right, because here the slope is negative, here the slope is positive, is not it? So, in other words, okay. So, in other words, if I am to the left of this line, the two molecules will attract each other, but if it crosses the equilibrium distance and they get closer than the equilibrium distance, then they are going to repel each other. Does that make sense? And so, what is my R equilibrium going to be then? Okay. Well, so I can take the differentiation. What will I get? I will get what? Minus 12a divided by r to the power 13, right? And then I will get a plus 6b divided by r to the power 7 is equal to 0. So, I end up with r to the power of 6 being equal to 2a by b, and so my R equilibrium will be then 2a by b to the power of 1 by 6. Does this make sense? Yeah. So, if I look at two liquid molecules for example, or two gas molecules for example, this R equilibrium comes in the range of, let us say, anywhere between 50 to 100 angstrom, okay, or 5 to about 10 nanometers, depending on whether it is liquid or a gas. Does that make sense? Okay. Now, consider a situation when these molecules are coming close to a crystalline solid. Okay. So, I have a crystalline solid and the atom spacing on this crystalline solid is, let us say, of the order of about 2 angstrom. Okay. So, these are my crystalline solid atoms, right. Now, what I just did was I figured that in the bulk far away from this wall, the liquid molecule spacing is, let us say, about 50 or let us say about 10 angstrom. So, the spacing between two liquid molecules would be 1, 2, 3, 4, 5, let us see 1, 2, 3, 4, 8, 9, 10. So, this is the equilibrium spacing between these two molecules, pretty far apart, is not it? But when you are coming close to the wall, if I look at this A and B parameter for the interaction between the solid atom and the liquid molecule or a gas molecule, this comes on the order of about 5 angstrom. Okay. So, I will see that my fluid molecules will be layering up as if they are a part of the wall because of the high attraction force. Solids typically have a higher energy of attraction, and therefore, the distance becomes shorter. Does that make sense? So, now I have these guys, they are probably spaced at about 5 angstrom distance on this direction and about let us say 2 angstrom spacing in this direction. Now, let me take a very big picture. So, this is a zoomed view, right. So, if I plot this on a much smaller magnification, and so if I have the wall, okay, what I will see is very close to the wall, I have formed a layer of liquid which has a very high density. Does that make sense? Because the density here is very low, the density here has gone up. So, this what I have just described to you is a physical adsorption on a surface. Okay. So, because of this physical interaction with the liquid molecules or the gas molecules with a solid surface, I am going to form this very dense layer close to the wall. Okay. In other words, if I plot the density as a function of distance from the wall, okay, something like kilograms per meter cube, let us say. So, what I will see is I will go through a very high density phase, and typically there is a sort of a oscillation before it goes to the theoretical value of density. This is your density value that you will get in your period in your property charts. Okay, that is your density in the bulk phase. But when you come very close to the surface, the density starts oscillating, and it usually is almost double the bulk value typically, and you can see it sort of decreases exponentially with distance. Okay, so keep this in mind, because we are going to talk about this thermal diode, and this concentration gradient that I have plotted using the red line over here, causes a thermal diode at the interface. Okay, that is what this model is telling us. Okay, and we will get into the discussion of the thermal diode a little later. All right, but what the Leonard-Jones, even a very very simple crude model like the Leonard-Jones potential, the implication is a density fluctuation at the wall. Now, when I am drinking water from a glass, the glass is very big, and so this ice layer that is forming, this ice layer is probably in the range of about let us say 10 to 20 angstrom, okay, the thickness, or let us say about 1 to 2 nanometers. And in certain cases there are literature reports where people have seen that this density oscillation can go as much as 20 nanometers with certain organic molecules, long chain organic molecules. Okay. So, people have done X-ray crystallography studies, and they have, the condensed matter physics community has shown that these kind of density oscillations exist between a solid and a liquid surface. Okay. Now, but the main problem is when you have a very big particle, if you have a 1 millimeter diameter copper particle and it has this 2 nanometers of ice around it, does not really matter, you do not feel it, right. But if you have a 10 nanometer particle and you have 2 nanometers of ice around it, now this particle has to drag that extra mass along with it as it is diffusing by Brownian diffusion or some other technique or other transport mechanism. This is that extra load that this particle now has to carry, right. So, because of this formation of this ice layer or the semi solid layer, we call it the compressed layer, the whole diffusivity of that particle changes, because now it has to drag that extra mass with it. Okay. And this ice layer that forms also has very interesting properties. Okay. It may not be the same as, it may not have the same property as the ice that you make in your refrigerator, okay, because of the nature of the structure of that ice. Okay. And we will get into that discussion a little later. but as a beginning, this is the implication of this model, which is I am going to form an ice layer. Okay. So, if I have a very big particle, well, the ice layer is just a thin skin on top, you do not even feel it. Okay. But if I have a 10 nanometer diameter particle, well, now I have 2 nanometers of ice around it, and that makes a big difference. So, that will now affect all the thermal properties, things like heat capacity, thermal conductivity, okay, diffusivity, even viscosity, because this is what I explained to you is a first order effect. Okay. In the second order effect, and we will see a little later, they start forming tentacles. This ice layer is not uniformly distributed. Okay. It starts developing these tentacles that grow in space and time, and they can grow and shrink depending on the situation you are dealing with. Okay. And we will get more into it when we talk about molten salts that is used in solar thermal applications, okay, in solar thermal power. So, that is as far as the Leonard-Jones potential is concerned. So, let us see, I think with respect to the Leonard-Jones potential, I wanted to show you a few graphs, a few pictures, and then okay. So, what I just described to you, oops, it is not showing up. So, let us just recap what we went through. So, this is what we described just now. You have the potential field, and then you have the force field, and you are plotting this as a function of the R, and so there is a difference between what is known as adsorption and absorption, one with a D and the other with a B, and what we just discussed is the one on the left, where things are getting assembled on the surface of an object. And depending on the pressure of the system and the number of molecules that is available in the system, what this graph over here shows is this ice layer, this semi-solid adsorbed layer can actually grow and shrink depending on the pressure and temperature of the system. And here is one other taken from the website, which shows that far away from the solid surface. Can I have the laser pointer, please? And so what this one shows is far away from the interface, the equilibrium spacing of the molecules is far apart, and then as you come closer and closer to the substrate, you can see the density of that particle has gone up. This is a very nice schematic that explains this concept. Okay. And so, if I have a nanoparticle, for example, on the right, you see that you can form this ice layer, semi-solid ice layer around it. Okay. So, now what is the implication? Okay. We were talking about convergence earlier, right? We are not just going to look at theory and fundamental science, but also look at how it affects our human activity. Okay. So, a good example where this is playing out in real life is in oil and gas exploration, particularly with respect to non-conventional oil resources, or what are known as shale oil. Okay. So, hydrocarbons that are trapped in shale rocks are being extracted by what is known as hydraulic fracturing. So, the way hydraulic fracturing works is, let us say a certain distance below the earth's surface, you have this very tight rock, very high density rock that is thank you. I do not need it, I just need the laser pointer. Thank you. So, so typically the interesting thing about shale rock, unlike other mining practices out there, let us say if you are mining coal, typically you have a very thick seam of coal that a person can stand in it, right. The shale rock can be as thin as a couple of feet in certain locations, and it can be maybe like 10, 12 feet thick at other locations, which makes the oil exploration very difficult, because you can drill pipes down here, but then you would need to drill pipes very close spaced, right, because each pipe can only access so much of gas. And so for a long time people knew that there was oil and gas in these shale rocks, but they could not extract it because the drilling technology was not there. Okay. And then horizontal drilling technology came along. Talking about convergence, there are key enabling technologies that have to come together, right, before something can become commercially feasible. And so once the horizontal drilling technique was implemented, so now they could drill and then go horizontal along the seam of the shale rock, and then they would pump water and a couple of other ingredients and fracture the rock. And once they fracture the rock, whatever hydrocarbon is stored in the pores of the rock, they diffuse out and it flows into the pipe, and now you extract it. Okay. Now the main problem is, if you look at this rock, for example, this particular SEM picture tells you, that's a 50 nanometer scale bar, right. So you can see the pores in the rock are very small. Here you see the pores are 15 nanometers, 8 nanometers, 21 nanometers. So if you plot the pore throat diameter and the percentage volume of this rock that has pores of, let's say, 10 nanometer, about 3% of this rock is 10 nanometers. Okay. 6% of the rock is 15 nanometers. Now the big question is the hydrocarbon that is stored in that rock, what is the density of that hydrocarbon? Okay. I know it's a certain distance below the Earth's surface, so I know the pressure, I know the temperature. So if I use a conventional PVT relationship, I can predict the density of this hydrocarbon that is stored in that rock, right. Turns out the density is actually much higher than what you are predicting using the PVT relationship. And the reason is because of that adsorption. The gas is adsorbed on the walls of the pore. Okay. And I just described to you that about 2 to 3 nanometers is the thickness of this adsorbed layer on a nominal basis. It can be higher than that, which means if I have a 10 nanometer pore, well, 2 nanometer from this side, 2 nanometer from this side, 4 nanometer is that hydrocarbon with double the density. Okay. And then remaining part is probably some kind of a liquid vapor mixture. And if you look at the properties of this particular fluid, it resembles a supercritical fluid. A supercritical fluid is one, it's a gas with a very high density, right, where you cannot distinguish whether it's a gas or a liquid, isn't it? So it has the properties of that of a supercritical fluid, even though the pressure and temperature is not supercritical. Okay. So that creates its own challenge in terms of how do you extract this oil or gas, economically. All right. So here is a molecular simulation. This shows that when you are in the gas phase, when you have very little of the hydrocarbon, the bulk of it is adsorbed on the walls. That's what the molecular simulation is showing you. And if you pack enough of these hydrocarbons in there, the density goes up, but again the density is much higher near the walls than in the bulk. Okay. So what is the implication of this? So here is a scale diagram. So let's say I have a 2 nanometer pore. If I look at typical hydrocarbons out there, so a carbon dioxide molecule will be, that's the proportion of the molecule with respect to the pore size. A single methane molecule, a single ethane molecule, a single butane molecule. You see there is not much of space left when I put in a butane molecule in there. Okay. So now how do we measure the properties in a lab? Okay. So we built an experimental apparatus where we put a chip with a nano channel in it. We went all the way from 50 nanometer, 10 nanometer, 4 nanometer, 2 nanometer. This was actually presented at the Society for Petroleum Engineering conference last year. Early this year essentially. So what we do is we make a nanofluidic chip with a single nano channel in there. I won't get into the manufacturing protocol here, we don't have time for that, but rest assured there are ways of making channels that thin. And so we mount it on a microscope and we illuminate it, and then we connect it with a syringe pump, and we pump hydrocarbons inside that nano channel, and then we heat it up to see when does it form a bubble, okay, or what is known as a bubble point. And of course, we have the whole image acquisition apparatus along with the computer, and so here are the results. Okay. So this is your boiling point of hexane. We pumped hexane in, and this is the theoretical value of the boiling point of hexane, close to about 340 Kelvin, roughly about 70 degrees Celsius. And so when we have a 50 nanometer channel, and we have a 100 nanometer channel, when we boil the hydrocarbon, the boiling point is very close to what the theoretical value is, or what the bulk value measurement is. But the moment I go below 10 nanometer to something like 10 nanometer or 4 nanometer, you can see there is a substantial increase in the boiling point. Okay, so the typical Peng-Robinson model, or the PVT model that is used, the Peng-Robinson model will predict this, and you can see clearly that there is a departure. Okay. So we did observations for 10 and 4. Currently we have data for 2 nanometer. We are trying to publish that paper right now. So the confinement effect is not significant. When I confine a liquid in a chamber, now the properties of that chamber affect the properties of the fluid. Okay, boiling point is a property, right? But you can see as I am shrinking the size of the chamber, the boiling point is changing. Okay, and the surface energy of this chamber starts affecting things like viscosity, thermal conductivity, heat capacity. So just think about it. It's very weird, right? The same fluid, I put it in different containers, and the viscosity is different, right? So that's the amazing part of multi-phase flows on the nanoscale, where the properties of the surface of your container start affecting the properties of the fluid. Okay, and so typically, if your pore size is more than 50 nanometer, you won't see it. This effect is there, but it's not very significant. But as you decrease the size of your container, for pores of 10 nanometer size and below, the pore confinement has a significant effect on the bubble point. All right, and later on Friday we will get into mixtures of hydrocarbons. I have some data, but this is just introducing you to the topic without making it too complicated for you. Let's go step by step in complexity, right? So on a very simple level, now if I'm doing with pure hydrocarbons, but what if I start mixing the hydrocarbons? And you will see the proportion in which you mix the hydrocarbons also affects this result here. Okay, so so there are a lot of interesting things that happen on the nanoscale. So in other words, normally if you go and look at your thermodynamic charts, they plot the values of the density or thermal conductivity or heat capacity. They do it as a plot as a function of pressure, volume, and temperature. You typically get a 3-dimensional plot, right? The interesting thing is there is a fourth dimension. There is a 4-dimensional phase behavior, which is the size of your container, the diameter of your pore. And as the diameter of your pore increases, these curves shift. That surface will shift. Okay, and so below 50, above 50 nanometers, you will get the same surface, and as you keep decreasing the size of the diameter, this 3D surface will keep moving. Okay, and so this is a completely new area, uncharted area. We need to come up with models where you can predict how these properties will change as you keep changing the size of the container. Okay, so so the approach we are taking, and this is a work in progress, we are doing experiments, we are doing equation of state models, we are seeing how much does it deviate from your equation of state model, and then we are making correction factor, and then once we have the correction factor, then we are doing a PVT simulation to generate these type of surfaces. Okay, so why do I need these type of data? Well, now if a drilling engineer or a production engineer wants to figure out how much oil they are going to produce, right, these type of simulation data helps them strategize the oil extraction procedure. Does that make sense? Okay, so so now the question is, how do you deal with these fluid interactions in the nanopore? Okay, so I just showed you the LorenzJones potential, right? One approximation typically people do in models is they instead of making it a complicated looking curve like this, they break it up into parts. So, in this part I can assume this is what the molecular potential is going to be. In the well over here I model it by a step function and then I let it go to 0 beyond the well. Okay. So, this is a very simplified abstraction of a LorenzJones potential. Okay. Now, the problem is the interaction this curve or this well that I have done between two molecules of the same kind is already known, but the biggest unknown is how does this molecule interact with the wall. For different types of rocks, this interaction potential will be different, and a priori when you are drilling you do not really know what the composition of that rock is. You know in specific locations where you have done the core extraction, but you do not know for the complete the geological formation that you are dealing with, because it is a very heterogeneous formation. Okay. So, these interactions between the hydrocarbons and the walls is something that is of an enigma, it is not completely known. Okay. So, that is where a lot of activities or effort is going into figuring it out, and that is one of the interaction topics we are dealing with in our lab as well, okay, along with my collaborators in petroleum engineering. So, when you confine things in a pore, this LC is the confined liquid, okay, the VC is the confined vapor, and VB is the bulk vapor. Okay. So, the vapor in the bulk, you can see the intermolecular spacing is much higher, but once you have a vapor trapped inside the nanopore, even that vapor property is different, okay, and then the liquid property is different as well. Okay. So, starting with a very simple model, the LorenzJones potential for example, you can see there are commercial implications that one has to deal with, in terms of what it is predicting and what the nuances are. Okay. So, let us see, do you all want to take a break now? Is this a good time for a break? Do you have tea or coffee or? Okay. So, do you all want to take a break and then come back, or should we continue? What do you all want to do? How many of you want to take a break? Nobody wants to take a break? All right. Well, then let us continue for another 10-15 minutes and then we will go for a break. Okay. So, let us see. Sorry. Now, coming to the topic of nanobubbles, I guess we did not get to discuss we stopped with heterogeneous nucleation yesterday, right? So, here is some interesting results from the literature. Okay. Somewhere in early 2000, 2004, 2000 time frame, people were doing atomic force microscopy, okay, of surfaces, and people were getting these sorts of weird looking the projection. I think the projection on the TV is better than the projection on the screen, right? I think so. If you look at the TV, it is much more clear, and what you see is these are scans of the roughness on a surface, and people were noticing these tiny spherical objects were showing up in their microscopy images. Okay, and then the big question was, what are these? Okay, so, with some investigation they figured these are small scale bubbles in a droplet of liquid. Okay, you have immersed this surface in a liquid and it is forming these very tiny bubbles in the range of about, let us say, 5 to 50 nanometers. Okay, now, if you remember, when we did the homogeneous nucleation theory or the heterogeneous nucleation theory, how much temperature drop will I need to sustain a bubble like this? Do you all remember the equation we used yesterday? So, what was the equation we used? Can somebody tell me? Okay. So, delta T is equal to 2 sigma by R, T saturation by rho G HFG. Okay. So, what did we say was sigma? Roughly about what, 60 times 10 to the power minus 3, right? And let us say we have formed a nano bubble with a radius of 10 nanometers. What is my T sat? Well, let us say about 373 Kelvin, right? How much did we say was the rho G? 0.5 kilograms per meter cubed, and HFG was what, 2.257 times 10 to the power 6. If you are a multi-phase flows guy, you should remember the surface tension and the HFG on top of your mind essentially. Okay. So, how much does this come out to? Can somebody quickly calculate and tell me? Nope. Now I have a 10 nanometer in the denominator. So, this one will come out, well, yesterday we said it was about 4 Kelvin, but that was 10 to the power minus 6 in the denominator, right. Now I have 10 to the power 9, so I am going up by a factor of 3. So, I need a 4000 degrees Celsius superheat to sustain a bubble that is 10 nanometers. So, according to this model, this bubble should not exist, but it exists. And not only that, people went back and did the scan like a couple of hours later, and it was still there. Yeah, sorry, somebody had a comment? But they go back and do the scan a couple of hours later, and the bubble is still there. If it was unstable, it should disappear in a few microseconds or milliseconds. Okay, so this was a big enigma in the community. How can this bubble survive? Okay, but yesterday we had the discussion. So, there are a number of ways you can criticize this data or criticize this conundrum that this bubble should not exist, but it exists, right. Number one, the 2 sigma by R equation, is it valid? Okay. So, first is validity of your Young Laplace equation. Okay. So, it is invalid because when we made the Young Laplace derivation, we assumed that the thickness of the interface was very small, and we neglected the volume of this interface, because we said that this radius of curvature was very high compared to the thickness of this interface. But when you are dealing with a nanobubble, this interface itself is of the order of, let us say, about 1 to 2 nanometers, and the radius of the bubble is 5 to 10 nanometers. So, the picture is more like this is my radius and this is my interface. That is the assumption behind the Young Laplace equation. Does that make sense? So, to begin with, the assumptions for deriving this equation are violated. So, this equation may not be applicable. Okay. The second criticism is the value of sigma, that surface tension value, this value in the bulk and this value in the local, are they the same? Okay. When I am dealing with a big bubble, I will get one value of sigma, but when I am dealing with a very tiny bubble, this value of sigma might be different. Okay. Why is that? Because no liquid is 100% pure. All liquids have some amount of impurity. Okay. So, if I have a big bubble, my impurities are probably very far apart. I might have, let us say, alcohol molecule or a grease molecule that might have diffused from the surface. Air has grease in it, coming from smoke, from pollution everywhere. Okay, and so some amount of it will dissolve in your liquid just because it is exposed to air, but it is a very tiny quantity, we normally do not see it. Okay, so if I have a big bubble, the impurities might be very far apart, but when I have a tiny bubble, okay, I have more number of impurities on the surface per unit area. So now, so what do these impurities do? They induce concentration gradients on the surface of the bubble. Okay, and whenever you have a concentration gradient or a temperature gradient, what happens to the surface tension? It goes down, right? As I keep increasing the temperature, the surface tension keeps going down. So similarly, as I keep increasing the concentration gradients or temperature gradients, the sigma goes down. So in other words, if I write down my sigma, it will be some sigma naught plus A1T plus A2T square and so on, right. Similarly, I can write this sigma as a function of concentration. So it will be some B1 times concentration plus B2 times concentration square and so on. And so when I am dealing with a nanobubble, this value of C, the concentration of that impurity is very high. Okay, and we are going to look at numbers when we look at molecular simulation data. Okay, and so because the C is very high, the surface tension of a nanobubble is probably much lower, maybe 100 to 1000 times lower than you would get for a big bubble. Okay, so these are all theories out there, nobody has really proven it, but these are ways you can rationalize the data. You see what I am saying? That theoretically something that is not supposed to exist is existing, so what gives? Okay, so that is the discussion about nanobubbles I wanted to have. So it is always a good idea to know the fundamental physics behind things and be conscious of the assumptions that led to an equation. Okay, and so if people are not conscious of the assumptions, they blindly apply that equation and they come up with ridiculous results that do not make sense. Okay, so that is why it is good to understand the derivation of equations, that way you know what assumptions went behind it and when it is valid and when it is not valid. Okay. So similarly, so what I just described to you over here is here in this chart, and I have taken this from a website and I have given you the reference, so you can go look it up. So here is your nanobubble, and of course there is a charge concentration that forms around the bubble or droplet, or for that, all that matter, this could be a nanoparticle too, a different phase, right. And so if you plot the potential, because of this charge concentration, you also create a potential gradient essentially. So if you plot the potential as a function of distance starting from the surface of this droplet or bubble, you can see the potential, there is a potential gradient, there is a concentration gradient, right, and so that would affect the properties of this surface tension. Does that make sense? And so here is actually a, so now the question is, what is the societal implication, the commercial implication of a nanobubble? Okay, so people are now envisioning that if I can make these nanobubbles on an industrial scale, I can do wonderful things with it. I can speed up chemical reactions by almost 100 to 1000 times. Okay, think about processing of chemicals. All right, people are thinking of using nanobubbles for things like cleaning up. Okay, if you have a nanobubble cleaning solution, it will be highly potent, but at the same time the environmental impact will be very low, because the nanobubbles will clean up the surface, form a big bubble and leave. Okay, instead of using a detergent that pollutes your water supply. Does that make sense? So if you go and check the pollution level in rivers, a good part of it is soap that is coming out from city discharges. Okay, or people taking medicine is actually showing up in drinking water now. Okay. So, but if you can make these nanobubbles in a very repeatable sort of way, there are lots of wonderful applications that you can do. So this is actually a very nice application of a multi-phase flows on the nanoscale. Okay, so I have a video that I wanted to show you, and And this is I put a lot of YouTube videos in these slides. You are welcome to go watch them in your spare time. Let's see. So, this is a video of these nanobubbles, they have been imaged in a microscope. Now, of course, these bubbles are below the wavelength of light. Your typical wavelength that we can see is what, 300 to 700 nanometers, but if the bubble is below 300 nanometers, how do you see it? Oops, what happened? Did you guys see the video or you didn't see it, right? Okay, my bad. I don't know why the video went out. Okay, now it's working. Okay, so let me show you the video once more. So now the question is, can you really see nanobubbles, or is this some kind of fake science? So the answer to that is these bubbles are below the wavelength of light, so you cannot really see it. But if you are illuminating it with a light, of course it will cause diffraction, and so what you are seeing is the diffraction image of the nanobubbles in this video. Okay, so let me show you another interesting video I have taken from YouTube. Actually, I might need sound for this one. Let's see. And you can see a microbubble is much less stable, right? If you form the microbubble in the suspension, within a few seconds it's gone. I don't know why it. So you can see on the right hand side, it's a continuous line that you can see because of the nano. Okay. Amazing, isn't it? All right. Now the question is, how do I form these nanobubbles? So one way to do it is using a porous membrane. Okay. Well, I'll let you watch these videos later on, but what it tells you is the properties have changed once you have formed nanobubbles in there. Okay. So let's look at this one final video, and you have the links in your notes, so you can go back and watch them later on. Unfortunately, the sound is not coming, but it sort of gives you an idea of how these nanobubbles are formed. Okay. Is it possible to get sound by any chance? Let me see, maybe I have muted my, no, mine is, It's not possible. Okay. So what they are saying is, let me back up a little bit. So what they are saying is, here are these nozzles. Okay, so you see this person holding a nozzle in their hand. Okay, that's actually a sort of a graphite material with lots of pores in it. Okay, and then when you pass a gas through it under high pressure, it forms nanobubbles. Okay, so you are forming this jet, and in the process this jet is actually generating nanobubbles. Okay. Let's see. So that's the nozzle. Come again? This is actually, I guess, one of these NHK TV channels. So this was a featured news article there. Oh, so they're trying to do cleanup. Yes, clean mud and sludge from water, for example. So let me see. So there was one image where they were actually making nanobubbles. Yeah, this is, you can see it here. So under high pressure, they're injecting the air into the water, and it's forming these nanobubbles right there. Okay. You can watch these videos in your spare time. In the interest of time, let's just stop here. Okay. So let's take a quick break, and then we will come back and start with the instability theories. All right.
shortcut question.
Sure, go ahead.
So if you neglect the volume because the radius of curvature is much higher than the radius, is much lower than the radius of the bubble.
No, so if your radius of the bubble is high,
you neglect the volume of the interface. Even though you are not taking it is sharp.
Right, right.
By the same logic, why don't you neglect the n, as in the number of particles inside it?
Because you're assuming, because then, the number of moles will be wrong, right? So you're not neglecting the mass, you're neglecting the volume.
So mass can't be neglected, but volume.
Volume, because there is no conservation of volume.
Okay.
But there is conservation of mass, right? So, I mean, it's an approximation to begin with,
So still happens.
Right. So, yes.
So the link for the material.
Yes, I need to forward it to you. So let me see. Remind me after when I take the lunch break. Okay. Now there is not much time for me to pull up the email. All right. So, but please remind me. Okay.
Yes,
so. Topic we are going to talk about is instability theory. Okay. So we are going to talk about linear instability first. Okay. So to understand the concept of linear instability, we need to understand the concept of wave theory. Okay. So just as a primer on waves, so let's say I have a wave on a surface. Let's say you throw up a stone in a pond and you are looking at the ripples in the pond, right? So this height of this ripple is your amplitude, eta, okay, and the wavelength going from one peak to the next peak is your lambda. Okay. So we use another parameter called wave number, which is defined as 2 pi by lambda. Okay. And then the phase velocity is your f times lambda. Okay. F is how many times per second is this node going up and down. Okay. How many, if I put a piece of foam or let's say a styrofoam on the surface, how many times does the styrofoam go up and down on that surface? That's your frequency, right? So this is known as the phase velocity. There is also something known as the group velocity, and we'll come to that in a second. So just like you have a wave number, you can also have what is known as growth rate omega, which is 2 pi times f. Okay. And so there is also something known as the group velocity, which is dk by d omega, and this one I can write it as let's see, omega by k. I'm sorry, I made a mistake here. So group velocity is d omega by dk. Okay. Now, in order for me to do this relationship d omega by dk or omega by k, I need to express my omega as a function of k, right? Well, f is not a good. Let's call it. No, well, phi is the potential function. That's the problem because we'll be using it. So let's say if I can express omega as a function of k, and this sort of a relationship is known as dispersion relationship. So physically, what does dispersion relationship represent? It represents that if I select a particular wavelength, at what rate is that wave growing with time or dissipating with time. Okay, so that's what the dispersion relationship expresses, because I can have very closely spaced ripples or I can have very gradual ripples. Now the question is, do all these ripples propagate at the same time, or do certain ripples propagate faster and certain ripples propagate slower? Okay. Or the other way to think about it, as your wave is growing up and down with time, is it dissipating with time or is it increasing with time? Okay. So, by doing a dispersion relationship, those are the type of questions we are trying to answer. Okay. So, that is why this linear instability theory is the first step in deriving that dispersion relationship, and then trying to figure out which particular waves will grow very fast and which particular waves will die down. Okay. So, that is the basic philosophy behind the whole instability theory discussion. Okay. So, let us start our instability theory discussion with the first type of wave we are going to look at, and that is known as a Rayleigh-Taylor instability. Okay. So, in a typical Rayleigh-Taylor instability, you have a very unstable situation, and the unstable situation is you have a heavier liquid okay, that is sitting on a lighter liquid. And so, what happens is the heavier liquid is trying to come down, right, and the lighter liquid is trying to go up, isn't it? And so, if this is the direction of gravity, for example, so this is my liquid rho L, this is my gas rho G, okay, and let us assume that it is going to infinity in this direction and it is going to negative infinity in this direction. Okay. And I am going to align my x axis along the direction of the propagation of the wave and y axis going into the heavier liquid. Okay. And I am going to make some assumptions. I am going to assume at the very, so I am going to do a linear stability analysis, which means I am going to drop all nonlinear terms. I am going to assume that all the nonlinear terms are so small that I can neglect them. Okay. So, and I am going to do a inviscid analysis. So, I am going to assume that the fluid is inviscid. I am not going to worry about viscosity, and I am to assume that these are incompressible liquids. Okay. I am going to assume, so linear stability means I have small disturbances. Okay, so what do I mean by small disturbance? If the amplitude of this wave is eta, and if the wavelength is lambda, I am going to assume that eta is much smaller than lambda. I am sorry. Okay, that is the assumption between for a linear stability analysis. So, in other words, I am going to neglect all the nonlinear terms, and I am going to assume that this is a stationary situation. So, there is no bulk motion. Okay, or no bulk motion essentially. So, if I write down the momentum and mass conservation equation for this situation, my mass conservation equation will be del u del x plus del v del y is equal to 0, where u is in the x direction and v is in the y direction, and I am going to assume this is a 2D situation. In other words, this wave is like a flat sheet of paper like this. Okay. In the z direction there is no variation. the only wave is in the x and y direction. Okay. So, I am going to assume it is a 2D wave. So, I can neglect the w component of the velocity, and so you can see that it is a very highly simplified analysis, but it gives you some of the key features that we are looking for. Okay. And then if you do the momentum equation, well, in the x direction your x momentum equation will look like del u del t is equal to minus 1 by rho del u del x, I am sorry, del p del x, and then in the y direction your momentum equation looks something like del v del t is equal to minus 1 by rho del p del y, and then there is a body force in the y direction which is your minus g. Okay. Because it is a inviscid flow, there is no viscosity, I can write this in terms of potential flow theory, and so my u becomes equal to del phi del x, my v becomes equal to del phi del y, and so the mass conservation equation becomes del square phi equal to 0, okay, where phi is my potential field for the velocity. Okay. So, now if I were to represent this wave, come up with the simplest equation for this shape of this interface, I can write it as this eta will be equal to whatever is the maximum amplitude eta naught times sin omega t or cos omega t, isn't it? Or I can write it in a more general form as e to the power of I times k x minus omega t, isn't it? Or I can write it as e to the power of I omega t minus k x, it does not matter, So, when you write minus k x, it means the wave is propagating in the plus x direction. When I write it as plus k x, it means the velocity, the wave is propagating in the negative x direction. So, at this point it does not really matter which direction the propagation is, all right. Now, the question is, what is the relationship between k and omega, right? That is what we are trying to hunt down. So, now even before we derive the solution, let us look at a few things. So, I wrote my eta to be equal to some amplitude times e to the power of I times k x minus omega t, right, and this omega can have a real component and a imaginary component, right. So, I can write my omega to be equal to omega real plus omega imaginary. So, if I have e to the power of I omega t, this becomes e to the power of I omega r, I am sorry, minus I omega t, do you all agree with me on this? Okay. So, the real component basically becomes cos of omega real t plus I sin omega real t, plus I will have e to the power of I omega I t. So, what does that tell you? The real part of my omega will not cause the wave to grow with time, it will just oscillate between a maximum and a minimum, but the imaginary component is the one, I am sorry, this becomes a plus, right. So, the imaginary component is the one that will make it grow with time. So, if my omega has an imaginary component, my wave is unstable, because the wave is going to grow with time. Is that clear? Okay. So, the imaginary part is the dangerous part, because that will cause my system to collapse, because the wave is going to grow exponentially in time. Okay. That is the crux of the instability theory. It is figuring out those waves for which the growth rate is imaginary. Okay. Make sense? So, now let us dive into the solution. Okay. So, since I assumed my eta has a form of I k x minus omega t, okay, the potential function phi will also then have a similar structure. So, I can say my phi will have a structure which is phi in the y component, and then I am going to have a e to the power of I k x minus omega t. Okay. So, if I now substitute del square phi equal to 0, okay, what will I end up with? I will end up with d2 phi dy square minus k square phi is equal to 0. And the solution to this equation, the general solution is phi y is equal to a1 e to the power of minus ky plus e2 times e to the power of plus ky. Okay. And now, in order for me to solve this solid problem, what are my boundary conditions? Well, I will have two sets of boundary conditions, one on the liquid side and one on the vapor or the gas side. Okay. So, the liquid side, what is the boundary condition? Well, my V of the liquid is equal to 0 as y approaches infinity, isn't it? Very far away from the interface, I will not have any ripples. Okay. And similarly, for the gas side, my Vg will be equal to 0 as y approaches negative infinity. So, if I apply these two boundary conditions, immediately I realize that my phi y is something like a l times e to the power of minus k y, and similarly phi y on the vapor side or the gas side is a g times e to the power of plus k y. Okay. So, in other words, if I write down my potential function for the liquid side and the vapor side, okay, my phi L will be something like a L e to the power of minus k y e to the power of I times k x minus omega t. Similarly, my phi g will be some a g times e to the power of k y times e to the power of I times k x minus omega t. Okay. Now, if I look at this ripple that is happening on the surface, right, and if I look at any particular height eta at any particular location x, the height of the wave at that location is eta. Well, let me draw it in a more magnified form. So, let us say this is my ripple on the surface, right. So, at any location x, this is the height of the wave eta, right. And so, at this location eta, let us say the velocity in the y direction is v star. Okay. So, v star is the value of the velocity when y is equal to eta, which means I am on the interface of the wave between the liquid and the vapor interface, and I can describe it as being equal to del eta del t, isn't it? It is a variation of eta with t, or I can write it in terms of my potential function, which is del phi L del y at y equal to eta, which should also be equal to del phi g del y at y equal to eta. Okay. So, if I solve for these, what comes out is my AL then becomes equal to eta naught omega divided by k times I, and what did I tell you, omega by k is what? It is the velocity of the wave, right. Okay. So, you can see that these amplitudes are related to the velocity, the wave velocity. Okay. And similarly, if you solve this equation for the gas side, you will see that the derivations are in the notes, you will download it from that link. So, it becomes eta naught omega divided by k times I, but it comes with a negative sign in front of it. Okay. Now, the final thing that we want to do is we want to integrate the y direction momentum equation. Okay. So, if I integrate the y direction momentum equation, okay, so what is my y direction momentum equation? It is del v del t is equal to minus del p del y times 1 by rho, right, minus g, isn't it? And so, instead of v I can substitute del phi del y, isn't it? So, it becomes del del t of del phi del y, it becomes minus del p del y times 1 by rho minus g. You all with me on this so far? Okay. And so, if I integrate this, then I will end up with del phi del t will be equal to minus 1 by rho times p minus some p naught, which is a constant of integration, minus rho g y. You all with me on this? Okay. And then I already know the value of phi. I can substitute the value of phi. I can do it for the liquid side, I can do it for the gas side, and then I can subtract one from another. Does that make sense? Okay. So, if I do that, the equation that I end up with is my dispersion relationship. Okay. So, what does the dispersion relationship look like? So, once I solve for the momentum equation, my dispersion relationship takes a structure that looks like this. Okay, because I solve this as a function of y. Okay. And remember, when I said that we are doing a 2D analysis, this is how my graph looks like, wave looks like. Okay. So, I have one curvature like this. What is the curvature in the z direction? Remember, when we were talking about a spherical bubble, there is a one curvature in the x direction, there is another curvature in the y direction, right. So, in this case I have a curvature, let us say, in this direction. What is the curvature in this direction? Infinity, right, because it is a straight line. Okay. So, what happens? So, when I write sigma delta p, so when I write delta p is equal to sigma times 1 by r1 plus 1 by r2, what happens to this 1 by r2 component? When r goes to infinity, this goes to 0. So, then my Pg minus PL is just sigma by r. Does that make sense? Now, the question is, what is r? Okay. So, this 1 by r is equal to del square eta del x square divided by 1 plus del eta del x whole square to the power of 3 by 2. Okay. This comes from coordinate geometry. And so, I can sort of write that, because we are doing a linear stability analysis, 1 by r is nothing but del square eta del x square, and so if I differentiate the equation for eta, which is I to the power of kx minus omega t, this comes out to be equal to k square eta. Okay. So, if I go back and substitute these equations, what I end up with is the final form of the dispersion relationship, and it looks something like this. Okay. So, if my minus omega square is positive, what happens? Omega becomes imaginary, and that is bad, isn't it? But if my minus omega square is negative, that is good, because then omega becomes real. Real omega is good, it does not go unstable. Okay. So, now the problem is what makes it unstable and what makes it stable. So, if I look at it, there are two components I am looking at, right. So, there is a positive component which is bad, because that will make the wave grow with time, isn't it. And then I have a negative component which is good, because that is making the wave stable. Okay. So, this is my stabilizing factor. This guy is good, it does not make the system unstable, and this guy is bad, because it is making the system unstable. So, if the first term is big, then system goes unstable. If the second term is big, it makes the system stable, right. So, where is that crossing point where it goes from stable to unstable? When omega is equal to 0. Okay. So, the value of lambda for which omega goes 0 is known as the critical wavelength. Okay. So, if I set omega equal to 0, my lambda is equal to lambda c and k becomes equal to kc, okay, and that is pretty simple, that is equal to let us see, rho l minus rho g divided by sigma, okay, and so that is equal to 2 pi by lambda c square, I am sorry, this is kc square. Okay. Or in other words, my critical wavelength lambda c is equal to 2 pi root of sigma divided by rho l minus rho g times g. Pretty simple, is it? Isn't it? Now, there is some philosophical discussion with respect to this solution. Okay. So, the philosophical discussion is something like this. So, you all know from your fluid mechanics classes, Reynolds number is a ratio of two forces, right. What are those two forces? So, inertia in the top and viscous force in the bottom. Okay. Now, we are going to discuss what is known as bond number, okay, and this is very important for two phase flow. And bond number is defined as the body force divided by the surface tension force. Or you can write it as the hydrostatic pressure divided by the capillary pressure. So, when I dive into a swimming pool and I go to a height h, what is the pressure? If I go to a depth h, rho gh, right. So, let us write it as rho g times L, that is my hydrostatic pressure. What is my capillary pressure if I have a bubble of a radius L? What is the pressure inside the bubble? Okay. Or in a 2D sense it will be sigma by L, right. Yeah, and is it really rho GL, or is it, if I put a bubble below, is it more like rho L minus rho G times the buoyancy force I am talking about, right. So, I can write this as in terms of the buoyancy force. Instead of writing this, I can write this as rho L minus rho G times GL, that is my buoyancy force, divided by sigma by L, is not it. So, when my bond number is greater than 1, the body force is bigger, is not it, and when my bond number is less than 1, that means my capillary pressure is bigger. And so, the dividing line is when bond number is equal to 1. Okay. So, if I put my bond number equal to 1, what value of L gives me that? So, I can write it out. I will get rho L minus rho G times G times L square divided by sigma is equal to 1. So, what is my that critical value of L? Sigma divided by rho L minus rho G times G, square root of that, and this particular length scale has a very good significance in boiling, and we usually denote it as L naught. This is the length scale in boiling, when your body force and capillary force are equal. And what did we say was our critical wavelength? Our critical wavelength was 2 pi root of sigma divided by rho L minus rho G times G. Do you see the philosophical link between the two? So, basically this is equal to 2 pi L naught is my critical wavelength, isn't it? Now, so I know the wave number at which my growth rate is 0 from the dispersion relationship, right. But then the next question is, which is the wave that grows the fastest? So, in other words, I have to take a d omega dk and set that equal to 0, isn't it? So, I go back to the dispersion relationship. Okay, so, if you remember, this was my dispersion relationship, right. So, I take the derivative of this relationship with respect to k and set it equal to 0. Okay. Now, there are two ways I could do this derivation, let us make this a simplified expression first before we take the derivative. So, if I look at it, I can take this equation and make it a non-dimensional equation. So, how do I make it non-dimensional? Well, then I will need a non-dimensional frequency, isn't it? So, let us look at a pendulum. We talked about the pendulum on the first day. A pendulum with a big string will oscillate slower, a pendulum with a small string will oscillate faster. It is the same thing in boiling. The refrigerants for which you have a big L naught will give you a big bubble, and the frequency at which the bubble will depart from the surface, form and depart, is going to be slower. And the refrigerants that form smaller bubbles or have a smaller L naught will have a higher frequency. Okay. So in pendulum what do we do? If I know the length scale, length of the pendulum, then T is equal to 2 pi root of L by G, okay, and then my frequency is what? 1 by T, isn't it? So that's 1 by 2 pi root of G by L, or my omega, which is 2 pi F, is equal to root of G by L. So let's do the same way over here. Okay, my length scale here is L naught, isn't it? So corresponding to this L naught, what is my omega, which is 2 pi F? Let's call it as root of G by L naught. That's one way to do it. Okay. The other way to do this same problem is to look at the dispersion relationship. Okay, so if I look at the dispersion relationship, let me recast it. Okay, so to begin with, my dispersion relationship was minus omega square. Okay, and what I can do is take this rho L minus rho G outside. Okay, so if I do that, I will have rho L minus rho G divided by rho L plus rho G. Okay, and then I will take the G out and I will divide it by L naught. You all with me on this? Okay. Then what will remain inside the bracket? Inside the bracket I will have K times L naught minus K cubed L naught cubed. You all with me on this? Yeah. And so this term that's outside the bracket, it has a G by L naught component, you see that, and this is just a ratio of densities. So I'm going to call this one my non-dimensional frequency, and I'm going to call this guy omega naught. Okay, so then the left hand side of my, and I take it to the left hand side, so now I am omega divided by omega naught square. So my left hand side is non-dimensional, isn't it? That will be equal to K times L naught minus K cubed L naught cubed. Okay, so now I am going to define a non-dimensional omega, call it omega star, which is equal to omega by omega naught. I am going to define a non-dimensional wavelength, which is lambda by L naught, and I am going to call a non-dimensional wave number K star, which is equal to K times L naught. You all with me on this? So what happens to this equation? My dispersion relationship in a non-dimensional form becomes minus omega square star, that's equal to K star minus K cubed star, isn't it? So minus K cubed star is a stabilizing guy, the surface tension makes it stable, the buoyancy force makes it unstable. So higher the buoyancy force, more chance of that amplitude growing with time, versus the surface tension is like kind of like a balloon, it's trying to push it down, and it's trying to prevent the wave, that lighter liquid, from rising up and the heavier liquid from sinking in, because surface tension is like a tough membrane. And so if there is high surface tension, it prevents the liquid from coming down, the membrane is tough. But if the surface tension is low, then the liquid more easily comes down. Okay? So surface tension stabilizes your system, buoyancy force destabilizes your system, and the waves grow with time. Okay? So now the derivation of the most dangerous wavelength, the wavelength that grows the fastest with time, becomes much easier, because now I can take the derivative of this. So I take the derivative of this with respect to K star. What do I get? Oops. what will I get if I take the, and you can see very clearly omega is equal to 0 when k star is equal to 1. So, k c star is equal to 1, which means my k is equal to let us see 1 by L naught, right, and therefore, my k c is equal to 1 by L naught, and so lambda c is equal to 2 pi L naught, is not it, comes out very beautifully from this non-dimensional form of the dispersion relationship. So, the next thing we do is we take a derivative of this with respect to k star. And we set it equal to 0, and this corresponds to the most dangerous wave number k d star, or let us call it k d. So, if I take the derivative, what do I get? I get a minus 1, let us see, sorry, plus 1 minus 3 k star square, right, and that is equal to 0. So, k star k d star is equal to 1 over root 3. You all with me on this? And therefore, in a dimensional form, my k d becomes equal to 1 by root 3 times L naught, 1 by L naught, or my lambda d becomes equal to 2 pi root 3 L naught. Okay, so, our lambda d is equal to 2 pi root 3 times root of sigma divided by rho L minus rho g times g. And lambda c is 2 pi L naught, or 2 pi times root of sigma divided by rho L minus rho g times g. Okay, now, what is the significance of this? Well, the significance is if I plot this omega, this dispersion relationship that I have for omega star as a function of k star, let us do a plot, right. So, if I do the plot, let us plot omega as a function of k. So, that is my k star, that is my omega star. I know at k star equal to 1 my omega goes to 0, right, and at k star equal to 0 my omega goes to 0, and I know when my value is 1 over root 3, it goes to maximum, right. So, I get something like this, and what is the value of omega star when this guy is 1 by root 3? Can somebody tell me? Because what I am plotting here is minus 1 over, actually let us do plot of minus omega square star. So, what happens when I substitute k star equal to 1 by root 3? What is the value of omega star? Give me a fraction. So, I will get what? 1 over root 3 minus 1 over 3. Come again? Okay, so that is equal to what? 2 by 3 root 3 in the denominator. Okay. Right. So, that would be 2 by 3 root 3 over here. Okay. I can do the similar plot, but instead of in terms of k star, I can do it in terms of lambda star. Okay. So, I have minus omega star square So, I will have 1, I will have root 3, and so the way the plot will look like is it will go to a maximum and then decrease. So, what that tells you is below the value of 1 the growth rate is zero, right, the imaginary part essentially. There is no imaginary part, it is all real. Okay. And at root 3, so all these waves that are below lambda star equal to 1 will die out in time. They are exponentially going to decay with time, and all the waves that are above wave number of 1 are going to grow with time, and particularly the wave that corresponds to lambda star equal to root 3 are the ones that are going to grow the fastest, and they are going to dominate the game, because they are the ones that will grow very quickly before the other waves can catch up. Okay, and that is the most dangerous wave. Okay. Now, what is the significance of the most dangerous wave? Okay. So, when your lambda is less than lambda c, okay, or your k is greater than kc, okay, you have a stable system, and if your lambda equal to lambda d or greater, okay, or your k is less than kc, okay, the system is actually, let us call it lambda c, the system is unstable because your omega is imaginary, and if omega is imaginary, my e to the power of I omega t grows in time. So, what is my maximum growth rate then? Okay. So, we found out that omega d is equal to 2 divided by 3 root 3, or in other words my the negative sign. So, my minus omega d square is equal to rho l minus rho g divided by rho l plus rho g divided by g divided by L naught times 2 divided by 3 root 3. Okay. Now, what is the physical significance of this relationship for lambda c and lambda d? You see this in your real life. Okay. These days there is a lot of rain. Once you go back to your room, look outside the window. You will have the ledge outside your window, right? After the rain ends, you will see droplets stuck to the ledge, and if you look closely, you will see the water droplets that are hanging are in a fixed periodicity. Have you noticed that? If your ledge is perfectly horizontal, you will see the water droplets. If this is your ledge and you look at the water droplets that are hanging, this is a fixed periodicity. So, let us predict what is the value of lambda d for water. Let us go ahead and do it. Okay. You will see there is an interesting thing that comes out. So, your lambda d is what? Equal to 2 pi root 3 times root of sigma divided by rho l minus rho g times g, isn't it? So, what did we say was the value of sigma was approximately 50, right, times 10 to the power minus 3. What is the typical density of water? 1000 kilograms per meter cube. Typical density of the vapor is about 0.5, so we can neglect it, isn't it? And what is your g? It is 9.81. Can somebody calculate what this comes out to? So, 2 pi root 3 is approximately equal to what? 2 times pi is 6, root 3 is 1.7. So, that is approximately 10 or 11, isn't it? And what is it that we have inside over here? 0.025 meters, which is 2.5 millimeters. No, it is 2.5 centimeters, I am sorry. So, roughly an inch, is not it? Go back and measure the distance between the droplets, you will see it is roughly an inch. That is a very strange coincidence, is not it? So, you have a Taylor instability situation, because the liquid droplet is a heavy phase that is trying to come down, the air is a lighter phase that is going to trying to go up. Okay. So, this lambda d also has, you will see that the bubble departure at diameter is very closely related to both L naught and lambda d. Okay. Let us do a very simple analysis. Let us say I have a bubble that is just about to depart from the surface. Okay. So, the buoyancy force Fb is trying to lift the bubble, the surface tension force Fs is trying to delay the departure. Okay. So, at the point your Fb just exceeds Fs, it will take off, is not it? Okay. So, what is my buoyancy force? Well, it is rho L minus rho g times the volume, which is what, pi d cubed by 6, yeah, times g, and what is the surface tension force that is pulling it back? It is sigma times d, is not it? So, what does the value of d come out? So, this is my bubble diameter at departure, is not it? So, how much is my bubble diameter at departure then? Sigma divided by rho L minus rho g times g, and I will have, well, there should be a pi here, right, it is the circumference. So, the pi's cancel out, and so I am left with a value of 6 over here, is not it? So, my bubble diameter at departure is what? L naught times root of 6, yeah. Or in other words, my bubble diameter at departure is proportional to L naught. And what is the departure frequency equal to? Come again, sorry. Any questions or comments? And what is the bubble departure frequency going to be? Well, it is going to be the omega d, because that is the rate at which it is going to grow the fastest, right. So, what is my omega d equal to? That is my omega d, right. So, the magnitude of omega d, if I look at the magnitude, that is going to be root of g divided by L naught times root of this density ratios, right, times root of 2 by 3 root 3. Well, this is approximately 1, this density ratio, because rho L is 1000, this is 0.5, this is 1000, this is 0.5. So, effectively this is 1, right. So, what is 2 divided by 3 root 3? How much is 2 divided by 3 root 3? Can somebody calculate? And if I take the square root of that, how much is it? About 0.8 roughly. Okay. So, my omega d is roughly 0.6 times g divided by L naught. So, without doing any analysis, I can directly predict, well, that is my omega. So, my 2 pi frequency will be what? This divided by 2 pi. So, it will be 0.6 divided by 2 pi root of g by L naught. So, without doing any particular analysis, as a back of the hand calculation, I can predict the frequency at which a bubble of a certain diameter d will depart. So, I can tell you that the bubble departure diameter is roughly proportional to L naught. Okay. So, a refrigerant with a high L naught will have a high bubble diameter at departure, and a refrigerant with a low L naught will have a lower volume for the bubbles that form, but the bubbles will form at a higher frequency. Okay. So, that raises a conundrum. Okay. So, let me talk about that conundrum. So, we are having a lot of philosophical discussions here, right. So, you can see by doing a very simple analysis without really caring for a very complicated equation, you can make predictions. You can actually design your experiments just based on L naught. Okay. If you know the L naught, you can design your experiment very quickly. All right. So, let us see. So, so let us say I want to estimate the amount of heat transfer I am going to get from a refrigerant. Okay. So, if I look at the surface where boiling is happening, I am going to get a lot of bubbles that are going to form and they are going to depart, right, is not it. So, how much is the energy in one bubble? How much heat is it taking? Well, if I know the volume of the bubble at departure times the density of the gas, that tells me the mass of bubble I have produced, and if I multiply it by the latent heat HFG, that is the amount of bubble energy that is going in one bubble. Now, if I multiply it by the frequency, that is the power in one bubble, that is the power rating of one bubble, is not it. And if I know the number of bubbles per unit area, I have predicted the amount of heat transfer I am going to get from my surface, right. Okay. So, what is Vd equal to? Well, that is pi dd cubed by 6 rho g HFG. What is my frequency equal to? G by L naught, and what did we say, 2 pi by 0.6 divided by 2 pi, right. So, that is about 0.6 by 6, roughly 0.1 essentially, is not it. So, the main enigma is how many bubbles am I producing per unit area and times the frequency. So, that is my power rating of my heater in boiling. Without doing any analysis, just from the instability theory, I know my dd, it is L naught. Okay. So, in essence, this becomes equal to some constant that comes from the pi by 6, 0.6 by 2 pi and all these things times L naught cubed times F times rho g HFG and times N. This I know. This I already know from my instability analysis. This depends on the surface roughness of your heater. How many cavities do you have per unit area on the heater? You can take a surface profilometer or an atomic force microscope, scan it out, figure out how many pits and grooves you have, you know the value of N. Without doing any analysis, you can predict how much heat transfer you are going to get in boiling. Okay. So, that is the beauty of instability theory. So, let us see, we did Taylor instability. What time is it? Let us take another 10 or 15 minutes, let us do Helmholtz instability, okay, in the Cartesian coordinates, and then we will go to the cylindrical coordinates after this one, okay, after lunch. So, that is the beauty of linear stability analysis. You do not need to do complicated CFD, just sitting down in a table you can make predictions, all right. Now, if you want to read on this, yeah, You know the Nobel Prize winning author Chandrasekhar? He actually wrote a very nice book on hydrodynamic instability. In fact, I pulled it up on the internet. You can go to your college library and see if they have a copy. Oops. Sorry, I want to show this video a little later. So that's the hydrodynamic and hydromagnetic stability by Chandrasekhar. I would recommend looking up this book. Okay. So what I gave you is, step 1 of instability. But if you want to read deep into it, this particular book is an absolute gem. Okay. So what I heard was Chandrasekhar worked on flow instability for about 10 years. He did research, and this book was an outcome of 10 years of his research before he moved to classical physics essentially. So anyway. So the next thing that we are going to look at is what is known as Helmholtz instability. Okay. Now why do I care about Helmholtz instability? Well, because Helmholtz instability applies to jets, and when you are close to critical heat flux, the bubbles, they join up in the vertical direction. Okay, and when they join up, they are formed a column. Okay, and so now if you have a column of liquid where the vapor is moving up and the liquid is moving down, if you have a pure cylinder, that pure cylinder is now going to go unstable and you are going to form ripples on that cylinder. The question is, what is the wavelength of that ripple and what is the growth rate of that ripple, because that tells us what kind of dynamics you have close to critical heat flux. Okay. So when we derive the equations for maximum and minimum heat flux, we will need the Taylor instability wavelength and we will need the Helmholtz instability wavelength and the corresponding frequencies. Okay. So let us do the Helmholtz instability first in the Cartesian coordinates, and then we will go to the cylindrical coordinates. Okay. So in this situation, what we have is what we had very similar to the Taylor instability. We have a ripple. Okay. Let us say this is the direction of gravity, and let us say this is my x direction, this is my y direction. Okay. And say it goes in the plus infinity in this direction and it goes to minus infinity in this direction. Okay. And once again I have at any particular distance x, the height of that wave is eta, and that eta changes as a function of x and as a function of time. If I fix x, it just bobs up and down at that location, isn't it? Except I am now going to make it a little bit more complicated, and I am going to assume that there is a velocity in this direction, a rho l and a ul, and I am going to have a rho g and a ug. Now it is one step more complicated than Taylor instability. In Taylor instability there was no velocity, in Helmholtz instability I have velocity. So all the same assumptions hold. It is 2D, the fluids are inviscid, incompressible, small amplitude compared to the wavelength, right. So that is why we are doing linear instability analysis. And of course once again my omega has two components. My omega is equal to omega real plus omega imaginary, and it is the imaginary omega that makes life complicated, isn't it. So but in this case there are certain differences. My v star, which is the velocity at y equal to eta, is equal to dy dt at y equal to eta. Okay, and so that is equal to d eta dt, right. V star is nothing but d eta dt, but now I am going to have two components because eta is a function of time and x. So I am going to have del eta del t plus del eta del x times del x del t. What is del x del t? It is my ul or ug, isn't it. So then my v star The only difference compared to what I did for Taylor instability with Helmholtz instability is in Helmholtz instability I did not have a velocity component, but in Helmholtz instability my velocity definition is u del eta del x. Okay, that is the only difference, and I go through the same motion as I did before. Okay, I write the potential function del square phi equal to 0 and so on and so forth, and so in essence I come up with a momentum equation, I integrate it in the y direction, and it is a very complicated number of steps. I am skipping it. You will have the handout, you can look it up there, and in essence what becomes is your you get a dispersion relationship. Okay, so the dispersion relationship looks something like this after I do the analysis. So my phase velocity c, which is equal to omega by k, okay, takes a very interesting form. So the interesting form is rho l ul plus rho g ug divided by rho l plus rho g. Okay, and then you have a plus minus I, actually let me write it in the second line, and then it becomes plus minus I times root of rho l rho g times ul minus ug square divided by rho l plus rho g square, and then you have the rest of the Taylor instability part, which is minus sigma by k divided by rho l plus rho g plus rho l minus rho g times g divided by rho l plus rho g times k. So in the Taylor instability, which one was the destabilizing guy? The last one, right? So this guy makes things unstable. This guy makes it stable, right? How about this guy over here? Does it make it stable or unstable? Well, rho l and rho g are positive. I don't know which one is bigger, ul or ug, I don't know, but the square of that is positive. So this is again a unstable term. Okay. Now the philosophical implication is very interesting. Okay, so if my ul minus ug exceeds a certain velocity, a certain value, it does not matter whether ul is big or ug is big, it is the difference that counts. Okay. So if the difference is very big, there is a certain critical value, and if you exceed that critical value, the system goes unstable. Okay. If ul is equal to ug, then things are fine because this goes to 0. Okay. Or if ul and ug are 0, then I recover Taylor instability back. Okay. So that is a good proof that my solution is correct. Now what about the term that is outside the square root? What is that? That is the average velocity, isn't it? If I do not have viscosity, I have one fluid phase moving with ul, the other fluid phase moving with ug, right? And so if I replace it with a equivalent fluid which has a density rho l plus rho g, that would be the mass average velocity of that equivalent fluid. And so this is what is known as a homogeneous model. I am going to replace two fluids with one fluid which has the average properties, and so the fluid with the average properties will have a velocity given by this. So this is nothing but your mass mean velocity of the interface. yeah. But but at the end of the day we want to figure out what is that critical condition. Okay, now let us consider a situation where the gravity instead of pointed along the direction of propagation, I am sorry, instead of going across the direction of propagation, let us turn it around. So, the gravity is pointed along the axis of the propagation, then that g is equal to 0 according to analysis, because now g has gone perpendicular to my original direction, isn't it? Okay, so if I set my g equal to 0, what am I left with? So, well, I can do it on this same piece of paper. So, if in this particular equation, if I set g equal to 0, all right, what am I left with? The terms under the square root sign are rho l, rho g, ul minus ug square divided by rho l plus rho g square minus sigma k divided by rho l plus rho g, isn't it? Okay, so this tells me what the critical value of this ul minus ug will be when there is no gravity or gravity is pointed 90 degrees to where we started. Okay. So, the critical value of this ul minus ug then comes out to sigma times k divided by rho l rho g times rho l plus rho g square root of that. Right? Go ahead. I am sorry. No, so all I am saying is, I am looking at a vertical jet. See, our original equation was the jet is in the x direction, gravity is in the y direction. But what if I turn the jet around? Now the gravity is along the jet. Or in other words, what is the g, if my jet is vertical, what is the component of g perpendicular to the jet? 0. So if I look at a vertical jet, then the third term disappears. Does that make sense? If I have a horizontal jet, then I cannot neglect that g component. But if it is a vertical jet, I can neglect the g component, because the component of gravity along the jet now is 0. You see what I am saying? Okay. So, or the component of g perpendicular to the jet is 0, I am sorry. Okay. So, let us look at that special situation, because when we get to critical heat flux, you have vertical jets, and I want to predict the lambda corresponding to that. Okay, makes sense. So, that is the case I am trying to get to. All right. Now, typically your k is nothing but 2 pi by L naught or some multiple of that, isn't it? Okay, so I can substitute this as 2 pi by L naught, right? And so if I do that, if I make that, it's an approximation, I'm trying to come up with an estimate, right? So let's make an estimate. So if I'm trying to make an estimate, I'm going to say my k is some multiple of 2 pi by L naught. If it is the most dangerous, it's 2 pi root 3, right? 2 pi by root 3 L naught. Or if it is the critical wave number, then it's 2 pi. All right. So if I go back and substitute k equal to kc, then my ul minus ug, the critical value, becomes equal to 2 pi sigma divided by L naught times 1 by rho L plus 1 by rho g. Okay. Just remember this relationship, because when we get to the maximum and minimum heat flux in boiling, this is a relationship we are going to need. Okay. Now, the big question is, if I have a jet, what is that wave number of that jet? What is that lambda? Here I have predicted that critical velocity difference, but I have not made a prediction for that wave number in lambda, right. So, in other words, a good example is you can go back to your room today, and in your bathroom you can do this experiment. You can take a faucet, and you can let the water drip down, right. Your water is going down, that is a liquid jet, and this jet is going to form ripples, is not it? Yeah. Now, if these ripples grow in time, eventually as the jet is going, these ripples are becoming bigger and bigger, and then you are going to form individual droplets. But if the ripples are decaying in time, if they are getting damped out, you will start with ripples, but the ripples will go smaller and smaller, and you will end up with a perfectly cylindrical spout of water coming out, is not it? So, now the question is, can I do an instability analysis for this configuration? Okay, because this has implications for my maximum heat flux calculation. Same thing, I am going to form a vertical jet, it is going to have ripples, and that ripple is going to break the jet up into individual bubbles, right. So, the key questions I want to answer are, once again, just like we did for Taylor instability or Helmholtz instability, what is this lambda, what is the growth rate omega, and how far do I have to go before the jet breaks up into individual droplets? Can I just sitting down with a piece of pen and paper do this prediction without ever doing an experiment? Okay, that is the question I am trying to answer, right. So, let us see, do you all want to do it now, or do you want to do it after lunch? It is 12:44. Let us go for lunch, and we will come back and answer that interesting question. Okay. All right. So, see you at 2:30. Thank you.